Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last few classes, we have been discussing about the angular momentum operator, its eigenfunctions. We have expressed angular momentum operator both in Cartesian coordinate and in spherical coordinate, and by defining the operators in spherical coordinate, we have also come to a situation of writing down the angular momentum eigenfunctions in spherical coordinates. For example, this is the expression that we derived in our last class, where this is one of the eigenfunctions of the angular momentum operator corresponding to angular momentum of L, where the m value, which is the second index, occupies the maximum possible value. So, where the when L and m both are equal, that is m is L, in that case the functional form of the eigenfunction of angular momentum takes this form. So, here we would see what happens when L is 0. So, when L is 0, m is also 0. So, therefore, psi 0 0 is n sin to the power L theta. Since L is 0, so this is 1, e to the power I L phi. So, since L is 0, that is also 1. So, psi 0 0, that means the angular momentum eigenfunction corresponding to L value 0 is simply n. And what is n? N is the normalization constant. What is its value? That we will try to get. To get this normalization constant, we must normalize this wave function psi 0 0. Remember, this function has theta and phi coordinate. So, we have to obtain psi star and we have to integrate this over all space. And what are the space available here? We have two variables, two coordinates, theta and phi. And if you remember, the element to integrate along theta axis is not just theta, rather it is sin theta d theta, and the element that we have to integrate for phi x coordinate is d phi. So, these are coming when we convert our dx, dy, dz, the volume integral in Cartesian space, to r theta phi, the spherical coordinate system. So, in this case the integral here is sin theta d theta, and for the case of phi it is d phi. So, when I look at this function psi 0 0, this is simply n. So, therefore, I have n square, and since it is a constant, I can go ahead and integrate the two functions. So, sin theta d theta, it goes from 0 to pi, d phi it goes from 0 to 2 pi. I already have done this in the last class. When I integrate sin theta, I get cosine theta, and I will put the limit up at 0 and pi, I would get this as 2, and when I integrate this, I get 2 pi. So, n square into 4 pi, if this function has to be normalized, this quantity has to be 1. So, therefore, n becomes 1 over square root of 4 pi, and psi 0 0 is nothing but 1 over 4 pi. Please note, here I have an eigenfunction which is independent of theta, which is independent of phi. So, there is no angular dependence on this function. We will come back to this property when we define some particular observable to this function. We will go on in our discussion of this wave function. What we would do is that we would take L is 1. So, therefore, I have one function, psi 1 1 is n, the normalization constant, sin theta e to the power I phi. So, here I have used L as 1 in this expression to get this functional form. Now, again I do not know what is n, this is what I am trying to get. I will do that by normalizing this function. So, I would do the same psi 1 1 star, psi 1 1, and I should not forget that the volume element has sin theta d theta d phi. So, when I use psi 1 1 star, I see that sin theta is a real function, its complex conjugate it's itself e to the power I phi is a complex function. So, I have to be careful when I evaluate its complex conjugate. So, I am left with n square. I would first write down the theta terms. So, sin theta for each for psi 1 1 and psi 1 1 star also sin theta. So, therefore, I have sin square theta, and then I am writing sin theta d theta, that is coming from the integral, and I am now dealing with e to the power I phi. So, its complex conjugate is e to the power minus I phi, e to the power plus I phi d phi, and this limit is 0 to pi, this limit is 0 to 2 pi. When I look here, this term e to the power minus I phi, e to the power I phi give me 1. So, therefore, this is 2 phi, and when I integrate this, this simply becomes 2 pi. This is easy. So, therefore, I am writing this 2 pi n square, and I have to deal now worry about this particular integration. When I have such a situation, what I would do is that I would express this as instead of writing down sin square theta, I will write it as 1 minus cos square theta sin theta d theta. So, this is 2 pi n square, the first term is 0 to pi sin theta d theta, the second term is 0 to pi cos square theta sin theta d theta. This term I have already seen a few times. So, this is its value is 2. So, I can write this as 2. And what about this? To solve this one, I would do this in this space. So, let us define cos theta as any variable t such that dt is minus sin theta d theta. When dt is minus sin theta d theta, so theta goes from 0 to pi. So, therefore, cos theta would go from cos 0 to cos pi. So, t would go from cos 0, which is 1, cos pi, which is minus 1. So, to solve this, when I look at this integral over here, so this is excuse me. So, this is t goes from 1 to minus 1. Now, I am left with t square dt. dt is minus sin theta d theta. So, this minus sign also is included in this term now. So, this is dt and t square dt. So, that you know as t cube by 3 goes from 1 to minus 1. So, minus 1 divided by 3 minus 1 by 3. So, that gives me minus 2 by 3. This is the result of this. So, 2 minus 2 by 3. So, 2 pi n square 2 minus 2 by 3 is this is 4 by 3. So, I have 8 pi n square divided by 3, and if this function is normalized, so the right hand side has to be 1. In this case, what is the value of n? N is 3 by 8 pi under square root. So, I got this normalization constant as 3 divided by 8 pi under square root, and I would use this form over here, and then I have the full the complete functional form of psi 1 1. Similarly, I can write down when L is 2, the function will be sin square theta e to the power 2 I phi and so on and so forth for higher values of L. And in each case, I can of course normalize the function. Now, this way of writing down the function, in this way I am actually getting, if for a given value of L, I have 2L plus 1 number of eigenfunctions, but this expression is valid for only one of these 2L plus 1. What about the remaining functions? The remaining functions we can obtain by using our knowledge about the step up and step down operator. So, what we have obtained already is that psi LL, which is the uppermost eigenfunction. So, you remember we had this space quantization concept. So, I am drawing these are the 5 eigenfunctions corresponding to L equals 2, for example. So, this is psi 2 2, this is psi 2 1, psi 2 0, psi 2 minus 1, psi 2 minus 2. Now, this functional form is valid for this when m is equal to L. So, when m is equal to L. How would I get 2 1 if I know psi 2 2? The answer is I have to apply L minus operator. So, when I apply L minus operator, I would get psi 2 1. How would I get psi 2 0? If I apply L minus operator one more time, I would get 2 0, and in this way I will get all other eigenfunctions if I know one of these eigenfunctions. So, this is the beauty of step up and step down operator, that I can, once I know one particular solution, I can create other states by simply applying this one of the step up or step down operators. Of course, you would see that this is the form of L minus operator. So, I have, when I apply on this function, so I have to take care of the differentiation with respect to theta, I have to take care of the differentiation with respect to phi, and this is mathematically going to be rather complex. The reason why we choose to discuss in the solution of angular momentum eigenfunctions in this way is that we can provide a general recipe as to how we can obtain different eigenfunctions, but what we will do next is that we will try to see what are the general solution of this angular momentum eigenfunctions. The general solution for this angular momentum eigenfunctions are known as spherical harmonics. The form of these spherical harmonics functions are given here. They may appear very scary to you, but do not worry about them. We would actually break this down for you, so that this form would be very meaningful for you. You can see there are so many terms here in this function. So, this is the general definition of the general form we represent spherical harmonics is that psi or y is often used. So, this is the functional the form. So, instead of psi we are now writing y, this is convention. Now, this has some L m terms, 1 minus x square. So, where x is defined as cosine theta. So, we know that theta is one of the coordinate that we have now, we know that. So, x is defined in terms of cosine theta, again some m, there is some p function that will come back, and then we see some e to the power I m phi. We will break this down, break this function down to some easier parts. What we see here is that the first few terms have only theta dependence. You see x has theta dependence. So, in this part of the term has having theta dependence, and this is actually the S term. If you remember, we defined our wave function angular momentum eigenfunction as product of two functions, one S of theta, another t of phi. So, this is the S function, S of theta, and this function is the t of phi function. The t of phi function is rather simple looking, but this S of theta is rather complex. The other thing that you would notice is that the t function depends only on one index, that is m, the second index of the spherical harmonics, or the second index of this angular momentum eigenfunction. On the other hand, the S function depends both on L and on m. We will discuss more about this S function now. If you look carefully, this S function has two components. The first component is simply the normalization factor. When we normalize this function, this would actually be the general solution of the normalization factor. If you remember, in the a few minutes ago, we tried to normalize this function, and we could do for psi 1 1, but for psi 2 2, if you try to do it, you would find that this process is somewhat lengthy, but here there exists the general form of the normalization factor. The other part of this S function is given here, which is known as the associated Legendre functions. Here these functions are associated Legendre functions. Again, do not worry about the long name. So, this function simply is 1 minus x square, x is cosine theta. So, 1 minus cosine square theta, the sine square theta raised to the power of m by 2, where m is your second index over here, and then you are differentiating m number of times depending on what is the value of m. You are differentiating m number of times a function which is PLX. This PL function is the well known Legendre polynomials. If you remember, in our harmonic oscillator discussion, we used the so called Hermite polynomials, and now what we are doing here in the while discussing the angular momentum eigenfunctions, we are using the something called Legendre polynomials. So, these are the Legendre polynomials that are given in most of the standard textbooks. So, the 0th order Legendre polynomial is simply 1. The first order Legendre polynomial in the coordinate of x is simply x. Since x is cos theta here, so P1 of cos theta is cos theta. The second order Legendre polynomial is 3x square minus 1 divided by 2. The third order Legendre polynomials is given by this. So, once we know these Legendre polynomials, we would differentiate that in m number of times and multiply this by this factor, and this would be called as associated Legendre function. The Legendre polynomials are given, and we can use them to obtain the associated Legendre functions. Once we have the associated Legendre function, by multiplying them with the normalization factor, we get this S function, and the T functions, T of phi functions are, as I said, they are rather simple in their expression. So, this is the general solution for the angular momentum eigenfunctions. What we do next is to write down a few angular momentum eigenfunctions using this general formula. First, let us start with the simplest of them, y 0 0. So, where L is 0, m is 0. When L is 0 and m is 0, then you can see 2L plus 1 here is 1, 1 over 2, L minus m, this is mod of m, absolute value of L, m. So, L is 0, m is 0. So, 0 minus 0 is 0, but this is you have to obtain the factorial of this term. So, factorial of 0 is 1, and similarly here 0 plus 0 and its factorial is again 1. So, therefore, 1 by 2 and this term is remains 1. So, under square root, and 1 minus x square, x is cos theta. So, therefore, 1 minus x square is my 1 minus cosine square theta. So, this is sine square theta, but raised to the power m by 2. What is m? m is 0. So, this is raised to the power 0. So, therefore, this becomes 1. Now, what I have to do is that I have to differentiate this Legendre polynomial of order L. What is L here? Since L is 0, so therefore, I will have to differentiate, I will have to write down P 0 x, and then I have to differentiate it with how many times? Actually 0 times. So, when I am, so this is d to the power d, I have to differentiate it m 0 times. So, therefore, its action is nothing, it is 1. So, I am left with P 0 x, 0th order polynomial is again 1. So, this is also 1, and finally, I have this last term where this is the t term, 1 over square root 2 pi e to the power I m phi, m is 0. So, therefore, e to the power is I 0 phi, and this term is also 1. So, now when I collect the terms that are left here, I would have 1 over 2 under square root, 1 over 2 pi under square root, and this is 1 over 4 pi under square root. If you remember, we had already derived this expression for psi 0 0. So, this general definition is this is how we have to use it. We will take one more example. We will take one more example where we will say for y 1 0, where L is 1, M is 0. That case what happens to 2L plus 1? L is 1. So, therefore, 3 by 2. L is 1, M is 0. So, this is 1 minus 0 factorial 1 1. So, this simply remains 3 by 2. 1 minus x square theta, this is sin square theta raised to the power m by 2, m is 0. So, therefore, this term will not contribute anything. Now, we will look at this differentiation. So, this is differentiation 0 times. So, this its effect is 1. So, I simply can write p function, the Legendre polynomial, which we do not have to differentiate because this is raised to the power m. So, p 1 of x, why do I write 1 here? Because this is p L and L is 1. So, p 1 x, and what is p 1 x? That is simply x, and x is our cos theta. So, therefore, this term I am replacing it as cosine theta, and then I look at the t of phi term and e to the power I m phi, and since m is 0, e to the power is 0, and this term is 1. So, what is the functional form? So, I have 3 So, this is the 1 0 function of which is an eigenfunction of angular momentum operator when L is 1, M is 0. Let us try to do this for y 1 1. When you do for y 1 1, here L is 1 and M is 1. So, L is 1, 2L plus 1 is 3 by 2, L is 1 and M is 1. So, therefore, mod of M is 1. So, 1 minus 1 is 0, factorial of 0 is 1, and 1 plus 1, and that is 2. So, that is factorial of 2. So, therefore, I am left with 2 3 by 4 under square root, and now I have to come to the second term 1 minus x square, which is x is cos theta. So, x square is cos square theta. So, this is sin square theta raised to the power m by 2, m is 1. So, this is 1 by 2. So, this is essentially the square root of this term, and now I have to differentiate this term, m is 1. So, mod m is 1. So, I have to differentiate it once, and what is PLX? PL is P1 of x, and what is P1 of x? P1 of x is x. So, when I differentiate, so this term is x. So, I have dx by dx. So, this term becomes simply 1, and now I am looking at the next term 1 over square root 2 pi e to the power I m phi, m is plus 1. So, when I collect this term, then I am left with 3 by 4 under square root, this is 2 pi under square root. So, I am writing 3 by 8 pi under square root, sin square theta, square root of sin square theta is sin theta, and e to the power I phi. If you remember, we obtained psi 1 1 as this form. So, what about y 1 minus 1, where L is 1 and M is minus 1 and not plus 1. When the effect of M is plus 1 or minus 1 is simply seen here. You see, in this case we are taking mod of M. So, whether M is plus 1 or minus 1, this term would not change. So, therefore, we can use the same term. What about here? 1 minus x square m by 2, but here m is also the absolute value of m. So, therefore, here this term also would not change. So, I am left with sin theta. What about this term? Again, since I am differentiating absolute value of m times. So, even when m is minus 1, I will have to differentiate this function once. So, therefore, I am getting the same term as 1, and finally, I am looking at the t term 1 over square root 2 pi e to the power minus I m phi. Here m In this case, it is not absolute value of m. So, here this would matter. So, when I collect the terms, I am left with so this way I can derive different forms of this angular momentum eigenfunctions, which are also known as spherical harmonics. I would suggest that you please use this relation and obtain the functional form of when L is 2, you will have 5 different values of m is -2, -1, 0, +1, +2. So, in this case you would actually be using, since L is 2. So, therefore, in that case you will be using P2x, the second order Legendre polynomial, and when you use m equals -2 or m equals -1, you have to differentiate this Legendre polynomials either 2 times or 1 times depending on what is your value of m. And when m is 0, then you do not have to differentiate, you just have to use this P2x. Remember, when you use P2x, you have 3 cos square theta minus 1 divided by 2. So, that exercise would enable you to use this general form of spherical harmonics and carry out your discussion. In the we would just conclude by showing you this general form of spherical harmonics. You would find them in most of the textbooks that you would be using. But when you derive your spherical harmonics for L equals 2, please see whether you are obtaining these values or not. In today's class, we discussed about the general definition of the eigenfunctions of angular momentum. We saw that the general solution of eigenfunctions of angular momentum are given by the spherical harmonics, which have 3 different components: one the normalization factor, one the S function which depends on theta, and another the T function which depends on phi. Taken together, we can now write down the spherical harmonics or the angular momentum eigenfunctions for any value of L and any value of m. Thank you for your attention.